Why nobody uses pneumatic mail anymore, a comprehensive historical and technical exploration part 1. Introduction A&D Foundational Concepts. Welcome to our in-depth exploration of one of the most fascinating and forgotten technologies of the modern era, pneumatic mail systems. For over a century, pneumatic mail represented the cutting edge of communication technology, promising to revolutionize how messages and small packages were transported through the heart of cities. It was a marvel of engineering that seemed poised to transform urban life forever. Yet today, barely anyone remembers these systems existed, and they have been almost entirely removed from the cities that once depended on them. This script will take you on a comprehensive journey through the rise, dominance, and ultimate decline of pneumatic mail systems, exploring why this once promising technology fell into complete obsolescence. Before we dive into the specifics of pneumatic mail, let's establish a clear understanding of what we're actually talking about. Pneumatic mail systems, also known as pneumatic tube systems or pneumatic dispatch systems, were underground or building integrated networks of tubes through which compressed air propelled small containers carrying mail and documents. These containers, typically cylindrical in shape and made of leather, wood, or metal, would be inserted into one end of a tube network and pushed through by air pressure to arrive at their destination sometimes mere seconds or minutes later. Imagine a system that could move a piece of correspondence from one part of a city to another faster than any human messenger could walk or run, operating day and night with minimal human intervention. That was the promise and, for many decades, the reality of pneumatic mail. The importance of understanding pneumatic mail systems goes far beyond mere historical curiosity. This technology represents a critical turning point in how humans think about communication, infrastructure, and technological solutions to problems. It also serves as a fascinating case study in how even the most sophisticated and well-established technologies can become completely irrelevant within a generation. The story of pneumatic mail teaches us important lessons about technological adoption, urban infrastructure, economic viability, and the unforeseen ways that other innovations can undermine even the most ambitious systems. The timeline of pneumatic mail spans from approximately the 1860s, when the first experimental systems were developed, through to the late 20th century, when most remaining systems were decommissioned. However, the peak of pneumatic mail usage occurred roughly between 1900 and 1960, when major cities around the world operated increasingly sophisticated networks of these tubes. During this golden age, pneumatic mail was seen not just as a practical system, but as a symbol of modernity and progress. It represented the triumph of human ingenuity and industrial might over the limitations of space and distance. Part 2. The origins and early development of pneumatic mail to understand how pneumatic mail systems came to be. We need to look at the specific historical moment in which they were invented. The mid-19th century was a time of extraordinary technological change. The telegraph had recently revolutionized long-distance communication. Railroads were transforming transportation. Gas lighting was replacing candles in cities. Against this backdrop of innovation, various inventors began thinking about how to solve a very practical problem: how to move documents quickly through increasingly crowded and congested urban centres. The first person to seriously develop a practical pneumatic tube system was William Armstrong, a British engineer who experimented with compressed air technology in the 1850s. Armstrong was primarily known for his work on hydraulic systems, but he recognized that compressed air could potentially be used to move small objects through tubes. However, the credit for creating the first practical pneumatic mail system generally goes to John Latting, an American inventor, and later, more significantly, to the French inventor Eugne Delporte, who patented a pneumatic tube system in 1866. But the most important early development came with the British engineer William Ramel, who, in 1863, established the first public pneumatic dispatch system in London. This system was revolutionary and captured the public imagination in a way that few technologies have before or since. The London Pneumatic Dispatch Company, as it was officially called, initially connected the General Post Office in St. Martin's Le Grand with the District Telegraph Office on Lombard Street. The tubes were about 4 inches in diameter, and the system could move small containers of mail with remarkable speed and efficiency. The technical design of these early systems was fascinating and, for the time, quite sophisticated. The tubes were typically made of wrought iron, joined together with lead and copper. A stationary steam engine would power an air pump, creating compressed air pressure that would propel the cylindrical containers through the network of tubes. Operators at various stations would load mail into the cylinders, insert them into the receiving tube, and then activate a valve that allowed the compressed air to push the cylinder forward. The process was remarkably fast. A message could travel from one end of the London system to the other in a matter of minutes, which represented an extraordinary acceleration compared to the traditional system of human messengers running through London's crowded streets. The London system was an immediate success and captured widespread attention. Newspapers wrote admiringly about the technology. Members of Parliament debated its merits and potential. Engineers travelled from around the world to study it. The system seemed to prove that you could move mail through a city reliably and quickly using nothing but tubes and compressed air. The operators working the system discovered various practical efficiencies and improvements. They learned how to manage air pressure to ensure smooth operation. They developed better connector designs to reduce leaks. They created more effective ways to seal the containers to prevent loss of pressure. During the 1870s and 1880s, the London pneumatic dispatch system was significantly expanded. New branches were added to connect more post offices, newspaper offices, and government buildings. By the peak of its operation in the early 20th century, the London system stretched for approximately 220 miles of underground tubes, connecting over 400 points throughout the city. This was an enormous engineering undertaking, requiring the construction of extensive underground infrastructure and the installation and maintenance of thousands of individual components. The success of the London system inspired other cities to develop their own pneumatic mail networks. Berlin established its system in 1876, Vienna in 1875, and other major European cities followed suit. Across the Atlantic, American cities were also embracing the technology. Chicago, Boston, New York, and Philadelphia all developed pneumatic mail systems. The United States Post Office even experimented with pneumatic tubes for moving mail over longer distances, though this proved less practical than the urban applications. Part 3. The technical mechanics of pneumatic mail systems. To truly appreciate both the achievements and the limitations of pneumatic mail systems, we need to understand exactly how they worked. The fundamental principle was straightforward: compressed air pushes objects through tubes. However, the practical implementation required solving numerous technical challenges that were far more complex than they might initially seem. Let's start with the tubes themselves. Early systems used cast iron or wrought iron tubes, typically ranging from 2 to 4 inches in diameter, though some later systems experimented with larger sizes. The tubes were laid underground in most cases, typically under city streets or running through the basements and lower levels of buildings. The decision to place tubes underground was both practical and aesthetic. Underground placement kept the ugly infrastructure out of sight, protected the system from weather and temperature fluctuations, and didn't interfere with the movement of people and vehicles on city streets. However, placing tubes underground also made maintenance more difficult and created issues with water infiltration and corrosion over time. The tubes were joined together using various methods depending on the period and location of installation. Early systems often used lead and copper joints with screwed connections. Later systems employed welded joints, which were both stronger and more resistant to leaks. The quality of these joints was critical to system performance. A single leaking joint could significantly reduce air pressure throughout an entire section of the network, causing delays and requiring investigation and repair. The containers that traveled through the tubes, sometimes called capsules or cartridges, came in various designs depending on the system and the era. Early London containers were typically cylindrical, about 4 inches in diameter and 6 to 8 inches long, made of leather with wooden end caps. Later systems experimented with various designs. Some used containers made entirely of metal, which were more durable but also heavier and more prone to jamming in the tubes. Some containers had springs or bumpers at the ends to prevent them from damaging when they arrived at their destination. Some had special seals to prevent mail from falling out during transit. The most critical component of any pneumatic system was the air pressure mechanism. Early systems relied on stationary steam engines to power reciprocating air pumps. These steam-powered installations were large, expensive, and required constant attention from trained operators. They had to be kept running continuously during business hours to maintain sufficient air pressure throughout the system. A failure in the engine or pump could shut down the entire network until repairs could be made. As technology advanced, the power sources for pneumatic systems evolved. By the early 20th century, electrical motors had replaced steam engines in most systems. Electric motors were smaller, cleaner, more reliable, and easier to control. They could be installed more easily in urban locations and didn't require the chimney infrastructure that steam engines needed. The shift to electric power represented a significant improvement in the practicality and efficiency of pneumatic systems. However, even with electric motors, maintaining constant air pressure throughout an extensive network of tubes presented significant challenges. The network had to be properly sealed, with all joints caulked and all external connections carefully controlled. Operators had to monitor pressure gauges throughout the network and make adjustments as needed. During peak operating hours, the demand for containers could exceed the system's capacity to propel them, leading to backups and delays. The sending stations, or injection points, were carefully designed to allow operators to insert containers into the system efficiently. A typical sending station consisted of a small chamber into which a container was placed. The operator would then close a valve and activate the system, allowing compressed air to push the container into the main tube at high speed. Different stations had different designs, but all shared the fundamental principle of using a small isolated chamber to accelerate the container to the speed of the airstream within the tube. Receiving stations, where containers exited the system, had to be designed to safely decelerate incoming containers. Containers arriving through the tubes could be traveling at speeds of up to 100 miles per hour, depending on the pressure and length of the run. Hitting a sudden stop could damage both the container and its contents. To solve this problem, receiving stations typically included a small chamber with springs or buffers that would gradually slow the container as it entered. Some systems used a secondary valve arrangement that would reduce pressure in the chamber as the container arrived, allowing it to decelerate gradually. This was a genuine engineering challenge that required careful design and ongoing maintenance to ensure it functioned correctly. Throughout the tubes, at regular intervals, there would be junction points and relief valves. Junction points allowed the network to branch out in different directions, creating a tree-like or network-like structure of connections. Relief valves allowed excess pressure to be released if the system built up too much pressure, preventing dangerous build-ups that could burst the tubes or create other safety hazards. These relief valves had to be carefully calibrated to maintain optimal pressure levels throughout the network. The size and complexity of large pneumatic networks meant that they had to be carefully planned and mapped. Cities maintained detailed blueprints showing every section of tube, every junction, every station, and every valve. These blueprints were technical marvels in themselves, sometimes covering entire rooms and showing thousands of connection points and components. Understanding and operating these massive networks required trained engineers and operators who understood the principles of the systems and could diagnose and fix problems. One interesting aspect of pneumatic mail systems was that their performance and reliability improved significantly as they aged and settled. New systems often had problems with leaks and pressure losses as components settled and connections shifted. After several years of operation, once all the components had settled into their final positions and all the joints had been properly sealed, systems often ran more smoothly and reliably. This led to the somewhat counterintuitive situation where older systems sometimes outperformed newer ones. Part 4. The golden age of pneumatic mail by the beginning of the 20th century. Pneumatic mail systems had become established features of major cities around the world. London, Berlin, Vienna, Prague, Paris, and other European cities had extensive networks. In North America, systems had been installed in New York, Chicago, Philadelphia, Boston, and numerous other cities. These systems were no longer experimental novelties, but rather integral parts of urban infrastructure. Mail and documents moved through these tubes constantly during business hours, and the technology had become so routine that most people thought little about it. The period from roughly 1900 to 1950 represents the true golden age of pneumatic mail systems. This was the era when they reached their greatest extent, served the largest number of people, and operated at their highest levels of efficiency and reliability. During these decades, pneumatic mail systems seemed like permanent fixtures that would continue to serve cities indefinitely. They were written about in popular magazines and scientific journals. They were featured in films and photographs. They represented modernity, progress, and the triumph of technological innovation. The volume of material moved through these systems during their peak years was enormous. In London alone, the pneumatic dispatch system was moving millions of pieces of mail and documents every year. The system operated nearly 24 hours a day, with only brief maintenance windows. Hundreds of people worked full-time in the system's operations, managing the various stations, maintaining the tubes and equipment, and coordinating the flow of mail throughout the network. The economic benefits of pneumatic mail systems were substantial. For businesses, the ability to move documents quickly through a city meant that transactions could be completed more rapidly. A lawyer could send a brief to a court. A merchant could send an order or an invoice to a supplier across town. A newspaper could send copy and photographs to its printing facilities. Pneumatic mail cut the time needed for these operations from hours to minutes. For large cities with extensive business districts, this represented a genuine competitive advantage. Insurance companies, stockbrokers, newspapers, and government offices were among the heaviest users of pneumatic mail systems. These businesses depended on rapid document transportation to function effectively. The ability to quickly send documents between branches or between different departments within a building was essential to their operations. As these businesses grew larger and more complex, their use of pneumatic mail systems generally increased. The system was also economical for the cities and operators. Once the initial infrastructure was in place, the ongoing cost of operation was relatively modest. An electric pump running during business hours used a moderate amount of electricity. Maintenance of the tubes and equipment required trained personnel, but was not excessively expensive. The cost per piece of mail moved through the system was quite low compared to alternative methods of document transportation. However, the system also had its limitations and problems, even during its golden age. The tubes could only carry small items. A container's maximum capacity was typically measured in dozens of pages or a few pounds of material. This meant that for larger shipments, other transportation methods still had to be used. The system could also experience bottlenecks during peak usage periods, particularly around midday or when major business transactions were occurring. If too many people tried to use the system simultaneously, there could be delays and backlogs. Maintenance and repairs were an ongoing necessity. Corrosion in the iron or steel tubes was a constant problem, particularly where moisture had infiltrated the system. Leaking joints would gradually lose pressure. Containers would occasionally jam in the tubes, requiring maintenance personnel to dig up the street or access the tube from a basement to extract them. These jams were not catastrophic, but were time-consuming and disruptive to service. Heavy or damaged containers would sometimes refuse to move through the system properly, particularly if they encountered any obstruction or if the pressure in the system was not optimal. The noise created by these systems was another issue that was often overlooked, but that was actually quite significant. The pressure valves and release valves created loud hissing sounds. The rapid movement of containers through the tubes created banging and rushing sounds. Building operators, station attendants, and residents in buildings near the tubes often complained about the noise. In some locations, acoustic insulation had to be added to reduce the noise level to acceptable levels. Temperature variations presented another challenge. In winter, the air in the tubes would contract, reducing pressure. In summer, the air would expand, increasing pressure. These seasonal variations required operators to adjust pressure settings throughout the year to maintain optimal performance. In extreme climates, additional insulation or heating systems were sometimes added to the tubes to reduce temperature-related pressure variations. Despite these various limitations and challenges, pneumatic mail systems continued to expand and improve throughout the early 20th century. New branches were added to networks in existing cities. New systems were built in additional cities. The technology was refined and improved. Larger tubes, more efficient pumps, better containers, and improved station designs all contributed to making the systems more reliable and capable. For several decades, it seemed that pneumatic mail systems would continue to grow in importance and capability indefinitely. Part 5. Pneumatic mail in major cities. To understand the true scope and significance of pneumatic mail systems during their heyday, we need to examine their implementation in specific major cities. These varied considerably in their design, extent, and technical specifications, reflecting different engineering philosophies and local conditions. In London, the pneumatic dispatch system was truly extensive and represents perhaps the best example of what a mature pneumatic mail network could achieve. By the 1920s, the London system stretched for over 200 miles of tubes and connected over 400 stations. The system was primarily owned and operated by the London Pneumatic Dispatch Company, which operated under a royal charter. The network was remarkably well organized, with regular service routes and predictable delivery times. A message placed into the system in central London could reach the opposite side of the city within 10 to 15 minutes. The system was particularly valued for its reliability, and operators took considerable pride in maintaining consistent service. The London system served a remarkable diversity of users: government offices, courts, post offices, newspaper offices, stock exchanges, banks, insurance companies, and private businesses all used the system. The volume of traffic was enormous, particularly in the financial districts. During the stock exchange's operating hours, enormous quantities of papers and documents moved through the system as brokers and traders executed transactions, and sent confirmations and documentation. The system had to be managed with considerable sophistication to handle this volume without creating dangerous pressure buildups or excessive delays. Interestingly, London had attempted to extend its pneumatic mail system to carry letters over longer distances. Starting in the 1870s, the post office had experimented with using pneumatic tubes to transport mail over distances of several miles. A special pneumatic tube service was established, and for a time it offered an expedited mail service within London. However, this service eventually proved less economical than expected, and the long-distance pneumatic mail experiments were eventually abandoned in favour of focusing on the shorter-distance urban distribution network. In Berlin, the pneumatic dispatch system took on somewhat different characteristics. The Berlin system began operations in 1876 and eventually grew to connect major government buildings, newspaper offices, and the main post office. The German engineering approach to pneumatic systems tended to be somewhat different from the British, with greater emphasis on precision and standardization. German designers were particularly interested in optimizing the mechanical design of containers and pump mechanisms. The Berlin system became known for its reliability and efficiency, and it continued to operate right up until World War II, when it was damaged during bombing raids and never fully restored afterward. Paris also developed an extensive pneumatic mail system, which had certain distinctive features. The Paris system was integrated into the existing pneumatic system for other purposes, such as moving small packages through department stores and office buildings. The integration of the system into the broader urban infrastructure meant that it had to be carefully coordinated with other underground utilities. The Paris pneumatic system, like systems in other French cities, employed somewhat different tube sizes and pressure specifications than some other European systems, which occasionally caused coordination problems if there were attempts to connect different regional systems. In Vienna, the pneumatic system was carefully designed to work with the city's existing underground infrastructure. Vienna's system also connected government offices, newspaper offices, and the main post office. The Vienna system was noted for the care taken in its design and construction. Austrian engineers designed beautiful receiving and sending stations, treating them as architectural features worthy of the elegant Austro-Hungarian Empire. Some of the surviving photographs of Vienna's pneumatic stations show them to be quite attractive, with brass fittings and decorative details that elevated them beyond purely functional structures. Vienna's system persisted longer than many others, continuing to operate in some form until the 1970s, making it one of the longest-lived pneumatic mail systems in continuous operation. This longevity reflects both the quality of its construction and the consistent support it received from the Vienna city government and the organizations that used it. In North America, pneumatic mail systems were built in numerous cities, with New York, Chicago, Philadelphia, and Boston being among the most significant installations. The New York pneumatic dispatch system was particularly extensive and served as a model for other American cities. The system connected the main post office, various branch post offices, newspaper offices, banks, and government buildings. The network was constantly expanding to meet the demands of the growing city. New York's system was noted for the substantial size of its tubes, some of which were 5 or 6 inches in diameter, allowing for the transport of larger containers than in some European cities. Chicago's pneumatic system was similarly extensive, connecting major business centers and government offices. The system in Chicago was designed to handle the enormous volume of business correspondence generated by the city's role as a major commercial and trading hub. The Chicago system operated with remarkable efficiency for many decades, and photographs from the early 20th century show it operating with steady, predictable service. In Philadelphia and Boston, pneumatic systems were also built, though they were generally somewhat smaller than those in New York or Chicago. Nevertheless, they served important functions in connecting government buildings, post offices, and major business centers. These systems generally operated without significant problems throughout the 20th century. Part 6. The technological refinements and innovations as pneumatic mail systems matured and operators gained experience with them. Various refinements and innovations were implemented to improve their performance, safety, and efficiency. These improvements demonstrate the ongoing commitment that engineers and operators had to making these systems work as well as possible. One major innovation was the development of sorting mechanisms at receiving stations. Early systems simply pushed containers to their destination, where they arrived in no particular order or organization. As the volume of traffic increased, operators realized that they needed to organize and sort the containers so that they could be efficiently distributed to their final destinations. Mechanical sorting systems were developed that could accept arriving containers, read or recognize addressing or routing information, and automatically direct them to the appropriate output chute or holding area. These sorting systems were mechanical marvels in their own right, using various combinations of gears, cams, and levers to perform their functions. Another significant innovation was the development of multiple pressure levels or zones within pneumatic networks. Rather than attempting to maintain uniform pressure throughout an entire network, operators realized that they could divide the network into separate zones, each with its own pump and pressure management system. This allowed for better control of pressure throughout the system and reduced the risk of pressure buildups or losses affecting a large area. The zones could be coordinated through manually operated valve systems, and later through more sophisticated pressure regulation systems. The development of improved container designs was another area of ongoing innovation. Early containers were quite simple, but as the systems matured, containers became more sophisticated. Some containers had improved seals to prevent mail from falling out or getting damaged during transit. Some had internal baffles to reduce movement of contents during acceleration and deceleration. Some had specialized designs for particular types of materials. Specialized containers were developed for moving film or photographs with careful cushioning to prevent damage. Other containers were designed for particularly valuable or sensitive documents. Station design also evolved significantly. Early stations were quite simple, basically consisting of a chamber with a valve and a push mechanism. Later stations incorporated more sophisticated design features. Some incorporated receiving buffers with graduated springs or pneumatic cushioning systems that would decelerate arriving containers more gradually. Some included mechanical readers that could automatically recognize addressing information on containers and direct them to the appropriate output. Some incorporated multiple input and output ports, allowing for greater sophistication in routing and organization. The control systems for pneumatic networks also became more sophisticated. Early systems relied on operators manually adjusting valves to send containers on specific routes. As networks became more complex, mechanical or electromechanical control systems were developed that could automate the routing of containers based on their addressing. These control systems used various mechanical mechanisms to recognize identifying marks on containers and activate the appropriate valves to direct the container to the correct destination. Pressure measurement and monitoring systems were another area of innovation. Early systems relied on simple pressure gauges that operators would check periodically. As systems became more complex, more sophisticated monitoring systems were developed. Some systems incorporated multiple pressure gauges at various points throughout the network, allowing operators to identify problems in specific sections. Later systems incorporated electrical transducers that could transmit pressure readings to a central monitoring station, allowing operators to monitor the entire system from a single location. Safety systems also evolved. Early pneumatic systems operated at relatively modest pressures, typically around 30 to 50 pounds per square inch. As technology advanced and operators became more confident in the systems, pressures were gradually increased to improve performance. However, higher pressures required more sophisticated safety systems. Relief valves were improved and more carefully calibrated. Rupture discs were added to pipelines to provide additional protection against dangerous pressure buildups. Operators developed procedures for safely inspecting and maintaining the systems. The improvement of electric motors represented another important innovation. As electric motor technology advanced during the 20th century, more efficient and more reliable motors became available. Replacing steam engines with electric motors not only improved the efficiency and reliability of pneumatic systems, but also eliminated the need for boiler rooms and chimney infrastructure in urban locations. This made pneumatic systems more practical and more economical to operate in densely built urban environments. Part 7. The challenges A&D limitations. While pneumatic mail systems achieved remarkable success and continued to operate for more than a century, they were never without significant challenges and limitations. Some of these limitations were inherent to the technology itself, while others resulted from changing circumstances and emerging alternatives. One fundamental limitation was the size of containers. The cylindrical containers used in pneumatic systems could not exceed certain dimensions without creating practical problems. Containers that were too large would not fit smoothly into the tubes, creating friction and pressure losses. This meant that the amount of material that could be moved in a single container was limited. For most systems, a typical container could carry perhaps 30 to 50 pages of paper or documents. For larger batches of documents or heavier materials, multiple containers had to be used, or alternative transportation methods had to be employed. The speed of pneumatic systems, while remarkable compared to human messengers, was limited by the design of the tubes and the pressure that could be safely maintained. Most systems operated at pressures in the range of 30 to 60 pounds per square inch, which resulted in container speeds of generally no more than 60 to 100 miles per hour. While this was very fast, it was not fast enough to eliminate the need for multiple containers or alternative methods for moving large quantities of material. Additionally, the time required to load containers, route them through the system, and unload them at the destination meant that the overall speed of the system was somewhat less than the raw speed of the containers within the tubes. The cost of constructing and maintaining pneumatic systems was substantial. Laying hundreds of miles of pipes underground required significant capital investment. The excavation work was disruptive to traffic and city life. The ongoing maintenance of such extensive underground infrastructure required trained personnel and spare parts. The energy cost of running electric motors or steam engines to power the air pumps was not trivial. While the cost per piece of mail moved was low once the system was constructed and operating, the initial capital costs were very high, and only large, prosperous cities could justify the investment. The physical limitations of the infrastructure created various operational challenges. Underground tubes were subject to water infiltration and corrosion, particularly in regions with high water tables or significant rainfall. Seasonal temperature variations affected system pressure and performance. Expanding cities meant that new construction sometimes damaged or disrupted existing pneumatic systems. The interconnection of pneumatic systems with other underground utilities, such as water pipes, electrical conduits, and sewer systems, created coordination challenges. In some cases, new construction would uncover and damage pneumatic tubes, requiring expensive repairs. The limitations of one-way transmission in many systems also created challenges. Some pneumatic systems allowed containers to move in both directions through the same tubes, using valves to control direction. However, in many systems, particularly early ones, the tubes were effectively one-way in practice, though technically capable of being used in either direction. This meant that stations had to be paired, with one station primarily sending and another primarily receiving. If you wanted to send mail in both directions between two locations, you needed two separate sets of tubes or a more complex valve arrangement. Weather and temperature could significantly affect system performance. In cold climates, the air in the tubes would contract in winter, reducing pressure and slowing container movement. In hot climates or during summer, the air would expand, increasing pressure. These variations could reduce predictability of delivery times and could stress system components. To compensate, some systems incorporated heating or insulation around the tubes, but these added to the cost and complexity. The noise generated by pneumatic systems was another significant limitation that is often overlooked in historical accounts. The rapid movement of containers through tubes, the operation of pumps and pressure relief valves, and the impact of containers on buffers at receiving stations all generated substantial noise. This noise could be particularly disruptive in residential areas or in buildings that housed offices or other noise-sensitive activities. Many complaints about pneumatic systems mentioned the noise, and in some cases, acoustic insulation had to be added, increasing costs and complexity. Operational errors could disrupt service. If a container became jammed in the tubes, the entire section had to be shut down until the jam was cleared. This could be time-consuming, as it often required digging up streets or accessing the tubes through basement access points. If a container came off the rails or became stuck, retrieving it could be difficult and expensive. Misrouted containers, or containers that arrived at the wrong destination, had to be retrieved and resent, reducing the efficiency of the system. Human operator error was another source of problems. Operators had to remember which routes to use for sending containers to specific destinations. As systems became more complex, this became more challenging. Operators who were tired or distracted might misdirect containers. If containers were mislabeled or the addressing was not clear, they could end up at the wrong destination. Training and maintaining standards was an ongoing challenge for system operators. Part 8. The decline begins the golden age of pneumatic mail systems, which had extended from approximately 1900 through the 1940s, began to show cracks in the 1950s. Various technological, economic, and social factors began to converge in ways that undermined the fundamental value proposition of pneumatic systems. While these systems would continue to operate in some cities for several more decades, the fundamental trajectory began to change during this period. One of the most significant challenges came from a source that might seem surprising: the rise of facsimile technology and eventually electronic communication systems. The development of the facsimile machine, or fax machine, represented a technological shift that directly competed with pneumatic mail for the function of rapid document transmission. Initially, fax machines were large, expensive, and not widely available. However, as the technology improved and costs decreased, fax machines became increasingly common in offices and businesses. By the 1970s, fax machines were becoming a standard piece of office equipment, and by the 1980s, they were nearly ubiquitous. The implications of fax technology for pneumatic mail systems were profound. The fax machine could transmit a copy of a document almost instantaneously over telephone lines. There was no need to physically move a container through tubes. There was no need to physically transport the original document. A copy could be transmitted at the speed of light, essentially instantaneously, for many types of documents and communications. This represented a dramatic improvement in speed compared to pneumatic mail systems. The economics of this shift were particularly important. Pneumatic systems required massive infrastructure investment, ongoing maintenance costs, and staff to operate. Fax machines required relatively small capital investment per machine and minimal operating costs. A business could place a fax machine in multiple locations and instantly transmit documents between locations without depending on a shared utility. This flexibility and independence from shared infrastructure was attractive to many users. Another technological factor that undermined pneumatic systems was the improvement and proliferation of courier services and local delivery systems. While human messengers had been common in earlier eras, they were expensive and slow. However, As motorcycles and automobiles became common, courier services became more practical and economical. A courier service operating motorcycles or small trucks could pick up documents from one location and deliver them to another location relatively quickly and efficiently. The economics of this approach became increasingly attractive as vehicle technology improved and fuel became cheap. Courier services offered advantages that pneumatic systems could not match. A courier could move larger quantities of material. A courier could pick up at any location and deliver to any location, without being constrained to the fixed network of pneumatic tubes. A courier could handle items that were too large or too delicate for pneumatic systems. The person receiving documents could see the delivery person and confirm receipt, which was important for legally sensitive documents or high-value items. Courier services could offer trackability and confirmation of delivery, which was important for security and liability purposes. The economic decline of pneumatic systems was also driven by the changing nature of cities and business. Many of the functions that pneumatic systems had been designed to support were becoming less important or were changing. Stock markets were automating, reducing the need for the physical transport of trading documents. Insurance companies were developing new systems and procedures that reduced the need for the rapid transport of documents. Government offices were becoming more dispersed, moving away from dense urban centers. The concentration of businesses in central business districts, which had been the norm when pneumatic systems were developed and had reached their peak, was being dispersed as transportation improved and businesses found it economically advantageous to locate in suburban areas or other cities. This dispersal made pneumatic systems less valuable because it reduced the density of users within the network and increased the distances that documents had to travel. A business in the suburbs could not use a pneumatic system designed for downtown. The growth of telephones and later telephone networks also contributed to the decline of pneumatic systems. While telephones did not directly compete with pneumatic systems for moving physical documents, they did compete for transmitting information. If you could quickly phone someone and communicate the necessary information verbally, or if you could send information over the phone using early fax technologies, you might not need to physically send a document at all. The cost of maintaining aging pneumatic infrastructure also became increasingly problematic. The tubes and systems that had been installed in the late 19th and early 20th centuries were becoming old and required more frequent maintenance and repair. Corrosion was an ongoing problem. Water infiltration damaged system components. Replacing large sections of aging infrastructure required shutting down parts of the system, which was disruptive and expensive. City governments and private companies that operated pneumatic systems had to weigh the costs of continuing to maintain these aging systems against the declining usage and the availability of alternative technologies. For an increasingly large number of systems, the economic case for continued operation became weaker over time. Part 9. The transistor, computers, A&D electronic communication, while the challenges to pneumatic systems began in the 1950s, the truly decisive blow came with the development of computer technology and, more importantly, with the development of electronic digital communication systems. These technologies represented a fundamental shift in how information was processed and transmitted. The transistor, invented in 1947 and gradually replacing vacuum tubes in electronic equipment during the 1950s and 1960s, enabled the development of smaller, more reliable, and more powerful electronic devices. Computers, which had previously been enormous machines filling entire rooms, began to shrink and become more practical for business applications. Data processing, which had previously required extensive manual work, could now be automated using computers. These developments had profound implications for business communications. The rise of electronic data processing created new ways of handling documents and information that did not require pneumatic systems. Businesses that had previously moved physical documents through pneumatic systems could now transmit data electronically between computer systems. The advantages were enormous. Information could be transmitted at the speed of electricity. It could be instantly available at multiple locations simultaneously. It could be stored, searched, and retrieved electronically without requiring physical movement of documents. The development of email systems in the 1970s and 1980s was particularly significant in undermining pneumatic mail systems. Email allowed written communications to be sent electronically, instantaneously, from one person to another. Early email systems were limited in scope, operating within individual organizations. But as email became more widespread, and as different email systems began to be connected together, email became an increasingly important method of business communication. By the 1980s, email had become the dominant method of business communication in many industries. The advantages were clear: instantaneous transmission, no physical transportation required, perfect clarity of the written word, ability to easily copy multiple recipients, automatic archiving of communications for record-keeping purposes. Compared to pneumatic mail systems, email was incomparably superior for most business purposes. The rise of personal computers and computer networks further accelerated this transition. As computers became common in offices, and as computer networks began to connect these machines, the ability to transmit documents electronically became increasingly standard. Software systems for document handling, version control, and distribution could manage the flow of documents much more effectively than physical transportation systems. The implications for pneumatic systems were clear. If a business could send a document through email in seconds, why would it place the document in a pneumatic tube and wait several minutes for physical delivery? The decision was economically obvious. Businesses began disconnecting from pneumatic systems. Usage declined. The economic case for maintaining the systems became weaker. Part 10. Changing urban infrastructure and city development. Another factor that contributed to the decline of pneumatic systems was the changing nature of urban development and infrastructure. Cities in the late 20th century were very different from cities in the early 20th century, when pneumatic systems had reached their peak. Suburban development and the dispersal of business and residential activities away from dense urban centers reduced the concentration of users that pneumatic systems needed to be economically viable. When businesses were tightly clustered in central business districts, pneumatic systems could achieve high utilization and justify their infrastructure costs. As businesses dispersed to suburban locations and to other cities, the density of users within the pneumatic networks decreased, making it harder to justify the ongoing infrastructure costs. The development of modern telecommunication networks also played a role. Fiber optic cables, which could be installed far more easily than the extensive underground pneumatic tube systems, provided capabilities for rapid data transmission that were far superior to what pneumatic systems could offer. Once cities began installing fiber optic networks for telephone and data communications, the infrastructure was in place to support electronic communications that made pneumatic systems largely redundant. Changes in urban planning and the improvement of roads and transportation networks also affected pneumatic systems. Improved roads allowed faster movement of vehicles and couriers. The development of express delivery services and specialized courier companies provided alternatives that were often more economical and more flexible than pneumatic systems. The rise of trucking and modern logistics meant that documents and packages could be moved across the city or across the country using vehicles rather than tubes. The growth of cities and the expansion of urban boundaries also created challenges for pneumatic systems. Extending the networks to new areas required substantial investment. The fixed networks that had made sense when cities were more compact became less practical as cities sprawled over larger areas. New development in distant suburbs could not be served cost-effectively by extending pneumatic systems across miles of undeveloped territory. Part 11. The environmental and safety concerns as the 20th century progressed, and environmental and safety concerns became more prominent in public discourse. Pneumatic systems faced additional challenges. While these systems had been designed with safety in mind, their design was based on standards and understanding that were developed in earlier eras and that seemed increasingly inadequate by modern standards. The issue of underground infrastructure in general became more problematic as cities became concerned about various environmental and safety issues. Underground pipes and tubes created various hazards and complications. If a pneumatic tube ruptured, the sudden release of high-pressure air could potentially create safety hazards. If a container became stuck in a tube, the system had to be shut down, and maintenance personnel had to access the underground infrastructure, which could be dangerous. Excavation work to repair or maintain the system could disturb other underground utilities and create safety issues. Environmental concerns about the aging infrastructure also became more prominent. Older pneumatic systems, many of which dated back to the late 19th or early 20th century, might have used materials that were no longer considered acceptable. Corrosion of metal tubes could potentially contaminate soil or groundwater. The desire to close or remove aging infrastructure that was perceived as potentially environmentally problematic provided another impetus for decommissioning pneumatic systems. Safety regulations also became more stringent over time. Pressure vessel safety standards evolved, electrical safety codes changed. Buried utilities had to be registered and marked so that excavation work did not damage them. Complying with these increasingly stringent safety regulations often required upgrading existing systems, which was expensive. For systems that were already becoming economically marginal, the cost of compliance with new safety regulations could tip the balance toward deciding to shut down and remove the systems entirely. Part 12. The last pneumatic systems and their closure, as the technological, economic, and regulatory environment became increasingly hostile to pneumatic mail systems during the late 20th century. One by one, cities made the decision to shut down their systems. The process was gradual and often took decades from the point when usage began to seriously decline until the system was finally decommissioned. The London pneumatic dispatch system, which had been one of the most extensive and most successful systems in the world, exemplifies this gradual decline and eventual closure. The system had operated continuously and reliably for well over a century. However, as electronic communications became more widespread and as courier services became available as alternatives, usage of the system gradually declined. By the 1960s, the system was operating at a fraction of its peak capacity. The decision to close the system was finally made in the 1970s. The closure itself was gradual, with different sections of the system being decommissioned at different times. By the early 1990s, most of the London system had been shut down and the tubes removed. In recent years, some of the remaining sections have been preserved or repurposed as tourist attractions or for other uses. Similar patterns played out in other European cities. Vienna's system, which had continued to operate longer than many others, was finally shut down in the 1970s. Berlin's system, which had been damaged during World War II, was not restored after the war. Paris's system was gradually phased out during the mid-20th century. Prague's system was decommissioned after the Soviet takeover of Czechoslovakia. Gradually, the extensive network of pneumatic systems that had existed throughout Europe in the early 20th century disappeared. In North America, similar patterns occurred. The New York system, which had been extensive and important to the city's business infrastructure, was gradually phased out during the latter half of the 20th century. Chicago's system was similarly abandoned. Philadelphia and Boston's systems were also eventually decommissioned. By the end of the 20th century, pneumatic mail systems had essentially completely disappeared from regular commercial use. However, it should be noted that pneumatic systems did not disappear entirely. Some specialized applications of pneumatic tube technology continued to exist and even thrive. Hospitals continued to use pneumatic tubes to move test samples, medications, and documents between departments. Banks used pneumatic tubes to move documents and cash between tellers and vaults. Some large government buildings and university campuses continued to use pneumatic tubes for internal communications. However, these were limited, specialized applications, quite different from the extensive urban networks that had characterized the golden age of pneumatic mail. Part 13. Why pneumatic mail ultimately failed. As we reflect on the rise and fall of pneumatic mail systems, several key factors stand out as having been decisive in their decline and ultimate failure as a primary technology for urban document transport. Understanding these factors helps us understand not just the history of this particular technology, but also broader principles about how technologies succeed and fail. The fundamental problem that pneumatic systems were designed to solve was the need to rapidly transport documents and small items through cities. In the late 19th and early 20th centuries, when pneumatic systems were invented and flourished, this was a genuine and important problem. The only alternative to pneumatic systems was human messengers, who were slow and expensive. Pneumatic systems represented a dramatic improvement over human messengers, and seemed likely to become the dominant method of document transport. However, the problem that pneumatic systems solved was a temporary one, dependent on the state of technology in a particular era. As other technologies developed and matured, they provided more elegant and economical solutions to the same problem. Facsimile machines provided a way to transmit documents electronically. Courier services using motor vehicles provided a flexible way to transport documents. Telephone and later electronic mail provided ways to transmit information without requiring physical transportation of documents at all. Critically, these alternative technologies were not constrained by the fixed network limitations that pneumatic systems faced. A fax machine could be installed anywhere a telephone line existed. A courier service could operate between any two locations. Email could connect any two individuals or organizations that had computer access. This flexibility made these alternatives far more practical and economical than pneumatic systems for an increasingly wide range of applications. The economics of the technologies also shifted dramatically. Pneumatic systems required enormous upfront capital investment in underground infrastructure. Once built, they were essentially fixed in location and configuration. Adding new destinations required expensive new construction. By contrast, alternative technologies could be deployed gradually, incrementally, and with much lower capital investment per unit of capability. The operating costs of pneumatic systems were also problematic. They required continuous power input and careful ongoing maintenance. Alternative technologies, particularly electronic communications, required minimal operating costs. Once infrastructure like telephone networks or computer networks was in place, the marginal cost of using them to transmit additional documents was essentially zero. The technological trajectory of the alternatives also favored them over pneumatic systems. Electronic communications technology improved dramatically and continuously throughout the second half of the 20th century. Computing power increased exponentially. Network capacity increased. Costs decreased. This continuous improvement made electronic communications increasingly attractive compared to the static technology of pneumatic systems. Another critical factor was the issue of obsolescence and technological lock-in. Cities and organizations that had invested heavily in pneumatic systems were investing in a technology that, while it worked well in its limited domain, was not progressing or improving. In contrast, organizations that invested in electronic communications or courier services were investing in technologies that were rapidly improving and expanding in capability. Over time, the gap between what pneumatic systems could do and what alternative technologies could do grew larger and larger. The environmental and regulatory issues that emerged as the 20th century progressed also contributed to the decline of pneumatic systems. These systems were perceived as aging infrastructure with potential safety and environmental issues. Complying with modern standards was expensive. for systems that were already becoming economically marginal. The cost of compliance often exceeded the economic value of the system. The dispersal of businesses away from dense urban centres was another important factor. Pneumatic systems had reached their peak value when businesses were tightly clustered in central business districts. As businesses dispersed to suburbs and satellite cities, the fundamental premise on which pneumatic systems were based became less relevant. The concentration of users necessary to make the systems economically viable no longer existed. Finally, there was an element of institutional and social change. The organizations and individuals who had operated pneumatic systems with pride and competence were retiring or moving into other fields. Younger engineers and technicians were being trained in new technologies. Newer organizations that were starting up were designed with electronic communications in mind rather than pneumatic systems. Over time, the knowledge, skills, and institutional commitment necessary Part 14. The Forgotten Infrastructure. One of the most remarkable aspects of the decline of pneumatic mail systems is how completely they have been forgotten. For modern urban residents, the existence of extensive networks of pneumatic tubes running under city streets seems like something from science fiction or fantasy. Few people today are aware that these systems ever existed, let alone that they once played an important role in urban infrastructure. This forgetting is particularly striking because the systems left behind extensive physical infrastructure that still exists in many cities. Under the streets of London, Berlin, Vienna, and other European cities, miles of pneumatic tubes still remain. Some are completely abandoned and sealed. Others have been repurposed for different uses. Some have been preserved as historical artifacts or museum pieces. But many are simply there, underground, a forgotten remnant of an earlier technological era. The reasons for this complete forgetting are worth considering. Part of it has to do with the nature of the infrastructure itself. Underground utilities are invisible to most people. Unless you dig up a street, you are not aware that the tubes are there. As the systems fell into disuse, fewer and fewer people had occasion to interact with them. Each generation that comes along knows less about the systems than the previous generation. Part of it also has to do with the rapid pace of technological change in the late 20th century. The changes from pneumatic mail to electronic communications happened relatively quickly, over a period of a few decades. People who grew up using pneumatic systems saw them disappear during their lifetimes. But younger people who grew up after the systems had disappeared may not even be aware they ever existed. The elderly people who remember using these systems have mostly passed away. The replacement of pneumatic systems with electronic communications also happened without conscious celebration or ceremony. Unlike the arrival of telephones or automobiles, which were marked by speeches and celebrations, the transition from pneumatic mail to electronic communications happened gradually and quietly. There was no grand event marking the passage of the age of pneumatic mail. There were no farewell celebrations for the systems as they were shut down. they simply faded away, and life went on. Modern cities have focused their attention and resources on other technological systems and infrastructure. The problems of urban transportation, communication, and utilities are solved using modern technologies that are far superior to pneumatic systems in most respects. There is little reason for modern urban planners or engineers to think about pneumatic systems. They are ancient history, replaced by systems that are faster, more flexible, more economical, and more reliable. Yet beneath the streets of many major cities, the remnants of pneumatic systems remain. In London, extensive sections of the original pneumatic tube network still exist underground. In Vienna, a small section has been preserved as a tourist attraction, allowing visitors to see an example of a pneumatic sending and receiving station. In Berlin and Paris, portions of the systems remain, some maintained for historical purposes, others simply abandoned. Occasionally there are efforts to preserve and document the history of pneumatic systems. Museums sometimes feature exhibits about the technology. Books and articles document the history of individual systems. The Smithsonian Institution has artifacts from pneumatic systems in its collections. But these preservation efforts reach only a tiny fraction of the population. For most modern people, pneumatic mail systems are simply unknown. Part 15. Pneumatic systems in modern specialized applications, while pneumatic mail systems have completely disappeared from urban document transport. Pneumatic tube technology has not entirely disappeared from modern applications. Various specialized uses of pneumatic tubes continue to exist, and in some cases have actually grown in the late 20th and early 21st centuries. Hospitals make extensive use of pneumatic tube systems to transport laboratory samples, medications, documents, and other materials between different departments and locations. These hospital systems operate on many of the same principles as the old pneumatic mail systems, but are designed specifically for the specialized needs of hospitals. Hospital systems typically operate at higher pressures and use smaller tubes and containers than the old postal systems. They often feature sophisticated electronic control and sorting systems that automatically route containers to the appropriate destination based on electronic addressing. The use of pneumatic systems in hospitals has actually expanded in recent decades. Hospitals have found these systems valuable for rapidly moving laboratory samples from collection points to testing labs, for distributing medications from central pharmacies to patient units, and for moving documents between departments. The reliability and speed of pneumatic systems is particularly valuable in hospital environments, where time-sensitive decisions must be made based on laboratory results. A pneumatic system can deliver a laboratory sample from a patient's bedside to the testing lab in seconds, which can be critical in emergency situations. Banks and financial institutions have also continued to use pneumatic systems in some cases. ATM machines in banks are sometimes connected to pneumatic tubes that can deliver cash or documents to different locations within a bank. Some bank vaults have pneumatic systems that can move documents or items between different secure locations. However, the use of pneumatic systems in banking has generally declined as electronic systems and modern security systems have become more sophisticated. Large government buildings and university campuses sometimes use pneumatic systems to move documents and materials between different departments or locations. These systems are typically limited in scope, serving a single building or a small campus rather than extending throughout a city. They are valued for their speed and reliability in these specialized applications. Some libraries have experimented with using pneumatic systems for returning books to different locations, though this application has generally not become widespread. The need to handle books carefully and the variability in book sizes make them less than ideal for pneumatic systems. Modern pneumatic systems designed for these specialized applications typically feature sophisticated improvements over the old postal systems. They often use plastic or fiberglass tubes instead of the iron or steel tubes used in historical systems. They feature electronic control systems that can route containers automatically based on electronic addresses. They include sophisticated pressure regulation systems that ensure smooth and reliable operation. They are designed for safety and environmental considerations that were not a priority in the original systems. However, these modern specialized applications represent a tiny fraction of what pneumatic systems once did. The idea of using pneumatic systems for routine document transport between different locations in a city is no longer considered practical or economical. Even in hospitals and other specialized applications, the use is limited to specific functions where the speed and reliability of pneumatic systems provides genuine advantages over alternative methods of transport. Part 16, Lessons from the Decline of Pneumatic Mail, the Rise and Fall of Pneumatic Mail Systems, offers numerous lessons that are relevant to understanding how technologies succeed and fail, and how to think about investments in infrastructure and technology. The first lesson is that even a well-designed and effective technology can become obsolete if a better alternative emerges. Pneumatic systems were genuinely well designed and operated remarkably reliably for over a century. But when electronic communication systems and motor vehicles provided better alternatives, the superiority of pneumatic systems became irrelevant. This suggests that investing in a technology, no matter how good, is a risky proposition if the underlying problem that the technology solves might be addressed more elegantly by future innovations. The second lesson is that flexibility and adaptability are more valuable than optimization for a specific function. Pneumatic systems were optimized specifically for the task of rapidly transporting small documents through cities. They did this task very well, but they could not easily adapt to changes in how that task needed to be performed or to new functions that users might need. Courier services, electronic communications, and other alternatives were more flexible and could adapt to changing needs. In modern technological landscapes where change is rapid, flexibility is often more valuable than optimization. The third lesson is that the network effects and flexibility of widely deployable technologies can outweigh the advantages of specialized infrastructure. Once telephone networks existed, fax machines could be deployed almost anywhere. Once computer networks existed, email could be used almost anywhere. These technologies did not require massive infrastructure investment or dependence on a central utility operator. Users could adopt them independently. This flexibility was ultimately more valuable than the slightly better performance of centralized pneumatic systems for their specific function. The fourth lesson is that the economics of infrastructure matter tremendously. Pneumatic systems required enormous capital investment and had substantial ongoing operating costs. Alternative technologies like electronic communications required much smaller capital investments and had lower operating costs. Over time, the economic advantage of the alternatives became overwhelming. Investments in infrastructure that requires massive capital investment and has high operating costs are vulnerable to being displaced by less capital-intensive alternatives. The fifth lesson is that technological trajectories matter. Pneumatic system technology was essentially static or improving only incrementally. Alternative technologies were improving rapidly. Over time, this different trajectory meant that alternative technologies became not just competitive, but dramatically superior. Investing in mature, stagnant technologies is riskier than investing in technologies with promising development trajectories. The sixth lesson is that technological progress is not reversible. Once cities became wired with telephone networks, once computer networks were installed, once courier services became established, there was no practical way that pneumatic systems could compete with these alternatives. The infrastructure investment in alternatives meant that the existing pneumatic systems, no matter how reliable they were, could not compete. The transition from one technology to another is generally permanent. The seventh lesson is that the death of a technology is often not dramatic or celebrated, but rather gradual and quiet. Pneumatic systems did not disappear in a day or a year. They faded away over decades as usage gradually declined, and system operators made pragmatic decisions to shut down aging systems that were no longer economically viable. This gradual transition meant that entire technologies could disappear with relatively little fanfare or awareness by the general public. Part 17. Cultural and historical significance of pneumatic systems beyond their practical importance. Pneumatic mail systems also have significant cultural and historical importance. They represent a particular vision of technological progress and urban modernity that was prominent in the late 19th and early 20th centuries. The pneumatic mail systems embodied a particular vision of how technology could solve urban problems. They represented the idea that major urban challenges could be solved through engineering and infrastructure investment. They were symbols of progress, modernity, and the triumph of human ingenuity over natural limitations. The tubes and containers became iconic images of a technologically advancing society. This vision of technological progress through infrastructure investment was particularly prominent in the late 19th century and the early 20th century. This was the era of major canal building, railroad construction, and urban infrastructure development. The pneumatic systems fit naturally into this pattern of thinking. They represented the idea that you could solve the problem of document transport in cities by building infrastructure that would carry documents rapidly from one place to another. However, this vision of progress through infrastructure investment was eventually displaced by a different vision of technological progress through information technology and electronic communications. The idea that you could move information through electronic networks at the speed of light was more powerful and more flexible than the idea of moving physical containers through tubes. Over time, this different vision of technological progress became dominant. Pneumatic systems also had significance as symbols of particular cities. Cities that had extensive pneumatic systems took pride in them. They were portrayed in photographs and descriptions of the cities as signs of progress and modernity. Building and operating pneumatic systems demonstrated that a city was technologically advanced and progressive. For cities like London, Berlin, and Vienna, the pneumatic systems were visible signs of their status as major cities at the forefront of technological progress. Pneumatic systems also influenced the imagination of architects and engineers. The underground networks of tubes represented a hidden technological infrastructure that existed beneath the surface of cities. This concept fascinated many people. Early science fiction stories sometimes featured futuristic versions of pneumatic systems. The idea of infrastructure existing hidden beneath cities influenced how people thought about cities and urban technology. Today, as these systems are largely forgotten, there is sometimes nostalgia for them. The mechanical elegance of the systems, the way they represented an earlier era's approach to solving technological problems, and the sense that we have lost something valuable by abandoning them, all contribute to a certain nostalgic appeal. Some people see pneumatic systems as representing a more elegant or craftsman-like approach to technology, compared to the more abstract and invisible digital technologies of today. Part 18. Preservation and documentation, despite the complete functional obsolescence of pneumatic mail systems. Efforts to preserve and document their history continue. These preservation efforts are important for maintaining awareness of this aspect of technological history, and for allowing future generations to understand how cities functioned in earlier eras. Various museums have exhibits about pneumatic systems. The Smithsonian Institution in Washington, D.C. has artifacts from pneumatic systems in its collections. The Science Museum in London has information about the London Pneumatic Dispatch System. Museums in other cities that had pneumatic systems sometimes have exhibits or collections related to them. These museum exhibits help to preserve awareness of the systems and allow people to learn about how they operated. Some cities have preserved physical remnants of pneumatic systems. In Vienna, a restored section of the pneumatic system is maintained as a tourist attraction, allowing visitors to see how the system worked. Parts of the London system have been preserved or documented. In some cases, removed tube sections have been saved and are stored or displayed to document the technology. Books and academic papers have been written documenting the history of pneumatic systems. Historians and engineers have studied individual systems in various cities, documenting their development, operation, and eventual closure. These written histories preserve detailed information about systems that no longer exist, and ensure that this knowledge is not lost. Photography and film documentation of pneumatic systems has also helped preserve their history. Photographs of the systems, their stations, and their operations have been preserved in archives and libraries. Some film footage exists showing the systems in operation. These visual records help document how the systems actually looked and functioned, preserving information that would otherwise be lost. Internet resources and digital archives have also helped preserve information about pneumatic systems. Websites devoted to the history of pneumatic systems gather information, photographs, and documents from various sources. Online forums and communities of enthusiasts discuss pneumatic systems and share information about them. This digital preservation ensures that information about the systems is accessible to modern audiences who want to learn about them. However, it should be noted that these preservation efforts are relatively modest compared to the scale and importance of the systems when they were operational. There is no major museum or archive devoted entirely to pneumatic systems. The efforts are scattered and decentralized. Many details about how systems operated and why they were eventually closed have been lost because no one systematically documented them. Much of the knowledge of the engineers and operators who maintained these systems has disappeared as they have passed away. Part 19, Comparative Analysis with Other Obsolete Technologies, the decline of pneumatic mail systems, is not a unique phenomenon. Many other technologies have experienced similar trajectories of initial development, adoption, growth, and eventual obsolescence. Comparing pneumatic systems with other obsolete technologies can provide insights into how technological change occurs. The horse and carriage is perhaps the most obvious comparison. For thousands of years, the horse and carriage was the primary technology for transportation of people and goods over land. It was highly developed, there were entire industries supporting it, and infrastructure was built around it. Yet within a few decades of the invention of the automobile, the horse and carriage became completely obsolete for most purposes. The transition was relatively rapid and dramatic, but it followed a similar pattern to the decline of pneumatic systems. An older technology, however well developed and reliable, was displaced by a superior alternative. The telegraph is another relevant comparison. For much of the 19th century and the early 20th century, the telegraph was the fastest method of long-distance communication. Extensive infrastructure was built to support it. Yet the telephone ultimately displaced the telegraph, despite the telegraph being cheaper and more reliable for many purposes. Eventually, electronic communication systems further displaced both the telegraph and telephone for many applications. This multi-stage displacement shows how a chain of technologies can successively replace their predecessors. Gas lighting provides another relevant comparison. Gas lighting represented a major technological advance compared to candles or oil lamps. Extensive infrastructure was built to supply gas to city streets and buildings. Yet electric lighting proved superior in most respects, and despite the existing infrastructure for gas lighting, cities gradually replaced gas lamps with electric lights. The installed base of infrastructure did not prevent the transition to the superior technology. The typewriter is another interesting comparison. For most of the 20th century, typewriters were the standard technology for producing typed documents. Offices invested heavily in typewriters and trained staff to use them. Yet the personal computer and word processing software ultimately displaced typewriters completely. The transition happened relatively rapidly once computer technology became practical and affordable. Television and newspapers provides another comparison. For much of the 20th century, printed newspapers were the primary source of news for most people. Extensive infrastructure supported newspaper printing and distribution. Yet television ultimately took over as the primary news source for many people, and now the internet is displacing television as the primary information source. Each technology was displaced by something seemingly better, despite the infrastructure and institutional support for the existing technology. What these examples have in common is that a combination of factors typically leads to the displacement of an existing technology. These factors include the development of a superior alternative, changing economics that favor the alternative, changes in how the underlying problem is defined or understood, the decentralization and flexibility of the alternative technology, and the eventual obsolescence of the infrastructure supporting the old technology. In all cases, the obsolescence was not inevitable in advance. Pneumatic systems like telegraphs, gas lighting, typewriters, and newspapers seemed like they would continue to be important for the foreseeable future. Yet in retrospect, their displacement by better alternatives seems obvious. This suggests that predicting which modern technologies will become obsolete in the future is extremely difficult. Part 20. Why nobody uses pneumatic mail anymore, the complete answer, after exploring the history, technology, and eventual decline of pneumatic mail systems, we can now provide a comprehensive answer to our central question: why does nobody use pneumatic mail anymore? The answer involves multiple interconnected factors that combine to make pneumatic systems obsolete. First, superior technologies for transmitting information and documents were developed. Facsimile machines, telephone systems, computer networks, and electronic mail all provided faster, more flexible, and more economical methods of transmitting information. Once these technologies existed and became widespread, the advantage of pneumatic systems disappeared. Second, the economics of infrastructure changed. Pneumatic systems required massive capital investment and ongoing maintenance costs. Alternative technologies like electronic communications required much smaller capital investments and lower operating costs. The economic balance shifted decisively against pneumatic systems. Third, the organizational and urban patterns that had supported pneumatic systems changed. The concentration of businesses in dense downtown districts declined as cities sprawled and businesses dispersed. This reduced the utilization rate of pneumatic systems and made them less economically viable. Fourth, the state of technology is constantly changing. Pneumatic system technology was essentially static, improving only incrementally. Alternative technologies were improving rapidly. Over time, the gap between the capabilities of pneumatic systems and alternatives became insurmountable. Fifth, regulatory and environmental standards became more stringent. Aging pneumatic infrastructure had to meet modern safety and environmental standards. Complying with these standards often exceeded the economic value of maintaining the systems. Sixth, there was